In this lecture, we'll learn about transmission electron microscopy. As the term suggests, that we are utilizing transmission mode of electrons to find out the features or see inside the material. So, in this particular case, we want the material to be transparent to electrons, so that electrons can really get transmitted through the material and provide some information about the material itself. And the way the electrons interact with the material is, like if we have a specimen around here, we can get some electrons which are inelastically scattered, and we can get them either as secondary electrons. We can also get them as Auger electrons. Some things can also get elastically scattered back after their interaction with the material, and those we can get them as a backscatter electron once we apply some incident electron beam. So, once we are applying electron beam, I can get some signal which are basically coming back either as secondary electrons or as Auger electrons or also as backscatter electrons. They can also interact with the material to produce something called X-rays. So, we can see that these are all everything is happening when the electrons can be detected, or those signals can be detected back above the sample regime. They are not allowing the electrons to pass through the material. But if we have a material transparent enough, if we can attain a specimen which is thin enough, and through which we can attain transparency for the electrons to pass through the material, what we can see is we can get the incident electron beam, we can let it pass through. The energy should be high enough so that it comes out as a direct beam, or it can also get inelastically scattered. So, we can also detect the inelastically scattered electrons, but we do not really need them. Why? Because once we are supplying certain kind of energy to the material, and if the electron is undergoing some inelastic losses, so we do not know what is the input. Though we know now what the output is, we will not know what the input is, the input energy of the electron. So, we will not know their wavelength, we will not know their overall functionality of how they are interacting with the material, but we are finally getting some signal. In some cases, we can also tap those particular signals, and we can it might also help in the analysis of the overall material, the structure of the material, or to track some sort of a crystallographic directions. But again, we can get much more information from a material if the electrons are getting elastically scattered. So, if I let my incident electron beam to interact with the material, and I let it elastically interact with the material, and I basically detect what are the elastically scattered electrons. So, now I know what is my input energy, I know how they will interact with the material to give me a final elastic interaction after their interaction with the material elastically. So, I know what is my output, I know what is my input, I can get much more information from the material after this elastic interaction has occurred with the material. So, that electron interactions, they can be very complicated in nature, starting from secondary electrons, backscatter electrons, Auger electrons. They can also start inducing some production of some X-rays, and that is actually everything is going back to the above the sample. But if all the signals are not really getting transmitted through the material, but if I let the electron beam be strong enough so that I can get some signals which are basically being transmitted through the material, I can get them as either direct beam, elastically scattered electron, or also as elastically scattered electron. And mostly I utilize this as my overall feature of analyzing a particular material, though I can also find some information from the inelastically scattered electrons as well. So, this basically comes under the transmission electron microscopy. First of all, what is the difference between my TEM and my XRD? TEM is a transmission electron microscopy. My XRD is the X-ray diffraction. So, generally we see that for a micron size particle, I always get some diffraction peak. So, in this particular case, I have my 2 theta. In this particular case, I have my intensity. So, for a nanocrystalline, for a microcrystalline material which has grain size greater than 1 micron, I will see some peak which is associated with a particular 2 theta value. So, I am getting certain intensity from the crystal after it has diffracted. So, I am getting some information, but as soon as the material starts becoming much more nanocrystalline or submicron size, then what happens? That my XRD is not able to detect whether I have some crystallinity into the material. It starts showing broadening of the peak, because as soon as my grains are becoming finer and finer, I start getting broadening of the peak. So, the device sharer crystallite size can be also calculated from the broadening of the peak itself. So, but here itself I am not, I don't know whether the broadening is either because I have a amorphous material or the crystals have become nano crystalline in nature. So, that complexity can be easily analyzed by TEM, and in TEM or the transmission electron microscopy, we can image and analyze all these nanocrystals. So, what I can get from electron diffraction is I can probe a very small area, that can be even a nanocrystal, and I can obtain a electron diffraction pattern, because now my beam is much more refined. I am letting the electrons interact with the material instead of an X-ray. Then X-ray will interact with the cloud of an electron or an atom as a whole. But my electron is so sensitive that once I am sending an electron to interact with the material, it gets affected even by a single electron or the positive charge which is there in the nucleus. So, I can see that I can get a very strong signal if I let my electron interact with the material, and now I can point it to a single nanocrystal, and that is what will give me out its diffraction pattern. So, in XID overall many grains contribute to the overall diffraction peak, but in my electron diffraction I can let a small beam of electrons to interact with a particular nanograin, and I can get a diffraction pattern out of it. So, that is the advantage of my transmission electron microscopy over the X-ray diffraction. So, what is so beautiful about this transmission electron microscopy is that electron interaction with the material is much more stronger. So, it is approximately 10 to the power 6 to 10 to the power 7 times stronger than those of X-rays. So, eventually my diffracted electron will have a very high intensity. As one more part we can see out here is the evolved sphere, which basically provides me the diffraction pattern. The radius of the evolved sphere is given by 1 by lambda. So, coming back to it, the wavelength in a TEM it is approximately 2 picometers, whereas in X-rays it is approximately 1 angstrom or 100 picometers. So, in this case I have 0.02 angstroms, and here I have around 1 angstrom. So, I can see that the wavelength part, it is much higher in X-rays, but in TEM my wavelengths are very smaller. So, eventually my evolved sphere which is being formed, so my 1 by lambda is very less. So, I get a much bigger radius for the evolved sphere. So, that makes evolved sphere much more flatter. So, instead of touching only few points, now once my evolved sphere is becoming much more flatter, I can see that more number of points now start interacting with the evolved sphere and they produce a diffraction spot. So, coming back to it, if we can orient a particular crystal for achieving a diffraction pattern, I can obtain all my diffractions within 0 to 1 degree, whereas for X-ray diffraction I have to rotate my crystal from 0 to 180 degrees to get a particular diffraction, because we know that 2d sin theta is equal to n lambda. So, as soon as I start reducing my lambda, I can for a particular interplanar spacing, obviously my theta is also getting increased with increase in the lambda. So, once I reduce my lambda to very large extent, my theta also will get diffracted. The diffracted spots will be very near, or they will be within a range of few 0 to 1 degree. So, that tells me that I can get all my diffraction pattern within a particular tilt of a particular plane, which is only 0 to 1 degree along the beam, that much parallel to the beam. So, if my beam has to be approximately parallel, because it is only 0 to 1 degree. So, my beam can be much parallel to the particular oriented crystal, and still it can produce a diffraction spot. It has to be within 0 to 1 degree, and that also will give me a particular diffraction pattern. And one more thing about it here is that since the intensities are very strong, because electron will interact very strongly with the particular matter, it is 10 to the power 6 to 10 to the power 7 times stronger. So, what I have to do, my exposure times automatically reduces to only a few seconds, whereas for taking an XRD spectrum, I spend 40 minutes, 45 minutes, an hour or much more than that to collect the overall spectrum of how my diffraction has really occurred. And also I limit it to a certain range, maybe say 0 to 180 degree or 20 to 90 degrees. So, I have to limit my diffraction angle to theta value, and then still it takes me couple of hours, whereas diffraction through TM, through electrons, it is much more rapid. I have to spend only 2 or 3 seconds to attain a spectrum. And so, since it is very rapid, I can see my electron diffraction pattern. I can directly view it on a fluorescent screen, or I can also collect it on a particular detector. So since my theta values are very narrow, 0 to 1 degree, I can orient my crystal along the beam direction, and just by tilting it marginally, I can also get a electron diffraction pattern. So that is the beauty of it. I can get a particular image. I can again orient my crystal only within a couple of degrees, and I can still get a diffraction pattern. And so I can get from diffraction pattern from a very small crystals also can be obtained, because my beam is very sharp, very intense. So I can focus it to a very localized location, or something called nano crystals. I can focus my beam into those nano crystals, and I can still get a diffraction pattern by particularly aligning the beam to a particular diffraction aperture. So I can direct my beam through a diffraction aperture, and I can still get a diffraction pattern from very fine crystals. As we know that electron cloud is scattered by the positive potential which is there in the electron cloud, whereas X-ray they interact with the whole of electron cloud. So these are the overall differences once we go from X-rays to TEM. That X-rays will interact with the major part of the material, whereas electron beam is much more sharper, much more intense. So it generally provides a very drastic or very high intensity information, and instead of focusing it to a very large area, I can focus it to a very fine area, and I can get diffraction pattern even from a very fine grain, or which can be a very fine crystal or a nano crystal. I can get my diffraction pattern within few seconds. I can view it directly on a screen as well, because it is so rapid, and I can also achieve all the diffraction within a tilt of 0 to 1 degree. So those are the advantages of TM in comparison to that of X-ray diffraction. And moreover, as we saw here, that the evolved sphere is actually so flat that many of the points they coincide with the evolved sphere. The reciprocal lattice points, they coincide with my evolved sphere to give me a diffraction pattern. And as we see here, that evolved sphere it comes out to be approximately 1.97 picometer. Once I have my energy of 300 kV electrons. So particularly coming back to the D value, which is approximately 2 to 3 angstrom for particular crystals. If I put this value in my Bragg's equation, 2d sin theta is equal to n lambda. So my lambda is known. Now my theta is also d is also known, because d is approximately 2 to 3 angstroms, and I can see that the theta value comes out to be 0.28 degrees only. So generally, as a rule, the scattering angles in the electron diffractions are very small. They vary between 0 and 1 degree. So I can see that my evolved sphere becomes very much flatter, because my lambda value is very less, and compared to that of lambda value of an XRD beam. So in my XRD, I use a wavelength of approximately 1 to 2 angstroms or so, which actually narrows down to less than it becomes around 2 picometer for 300 kV electrons, and that basically brings down the scattering angle to around 0.28 degrees. So eventually my scattering angles are very small in transmission electron microscopy. So there are certain rules. I have my incident electron beam. It interacts with the lattice planes, and it gives me a diffracted beam at an angle of 2 theta. And since my theta values are very low, the reflecting planes are almost parallel to the direct beam. So that's what we can see, that my beam which is getting diffracted, it is tilted only at very fine angles of 0 to 1 degree. So they are almost parallel to the direct beam. And secondly, the incident electron beam, the beam which is basically falling onto the particular to interact with a particular lattice plane, becomes the zone axis of the reflecting set of lattice plane, because it is approximately perpendicular to the plane which is basically it is interacting. So the normal to it will be perpendicular to that, and my electron beam is again perpendicular to the normal of the particular plane. So my incident electron beam becomes the zone axis. So this becomes the zone axis in terms of defining all the other diffraction planes. So that is those are certain rules which are being followed out here, that my reflecting plane is parallel to the direct beam, and secondly my incident electron beam becomes the zone axis of the reflecting set of lattice planes. So because there will be so many lattice planes, so this incident beam becomes the zone axis for all such planes. This is the overall construct of a particular TEM, transmission electron microscope. that initially I have a source for the electron, source or electron source. Here I generate my all the electrons. Then I have set of magnetic electromagnetic lenses. These are certain condenser lenses, generally 3 to 4 condenser lenses are utilized. Then I have my condenser aperture along this particular part, so it is required for the alignment part. And then I have my objective aperture, objective condenser lenses out here. Then I have my objective aperture out here, and this is what decides the overall resolution of my TEM. Then again I have some objective lenses. Then again I have selected area aperture, and then again I have some diffraction lenses, I have intermediate lenses, I have projector lenses, and I keep my sample actually in between, which I will come to in the next slide. But this is the overall construct of a TEM, that I have my electron source, a set of electromagnetic lenses, first the condenser lenses, and then my objective lenses, and then the projector lenses, to finally get a image. So I can see out here, if I keep my specimen at this particular location, I have it already passed through the condenser lens. So I can see that my specimen is at particular location, and then I have my objective lens, which basically gathers information from a particular specimen. So electron beam comes, interacts with the specimen, and that information is being collected by the objective lens. These are not really some tangible or something like optical. They are not like optical lenses. They are more of electromagnetic lenses. So there is nothing hard as such as we see in the optical microscopy, that we have really glass or lenses which are guiding the light. But in this particular case, we have electromagnetic lenses which are directing the electrons. So once I collect the information, so I can see I have my objective lenses which is gathering the information from the specimen after the electron beam has interacted with the specimen. Then I can see I have an intermediate, which is called intermediate diffraction pattern, which where what I call back focal plane. Here I form my intermediate diffraction pattern, or later on I can also form a intermediate image plane. So this is a image plane, and this is my back focal plane. So if I keep my aperture at the back focal plane, finally what I get is an image, and if I keep my aperture at the image plane, finally what I get is the diffraction pattern. So I can see that I am forming my intermediate image at the certain location. So I can have aperture. One thing is called objective aperture, or something called back focal plane, objective aperture. So here I am forming my diffraction pattern, and if I keep my aperture at this particular location, I can get bright field or dark field image. Or at the second location where I have something called SAED aperture, here I am forming my intermediate image, and if I keep my aperture out here, what I get is a diffraction pattern. So these two are more complementary kind of features which I can really tap, and I can form an intermediate image as well. So I can form my intermediate image or intermediate diffraction pattern to finally get a image or a diffraction pattern. My viewing screen can be the fluorescent screen on which electrons can interact and they can come and fall, or it can also be a CCD camera. So I can see that I have a particular specimen. I let the electron beam pass through condenser lenses, then it interacts with the particular material, it passes through, and then I have a set of objective lens which gathers the information and lets it through a certain apertures. It can be at the back focal plane, or it can also be at the image plane, and depending on where I choose my aperture, I can get if I keep my aperture at the back focal plane, I get something which some image. If I keep my aperture at the image plane, I get a diffraction pattern, and in between I can have some intermediate lenses for basically magnifying a particular image or a particular image. So that's what I can see in this particular construct or the ray diagram. So essentially, to construct a TEM, my first requirement is the electron gun, because I need to generate electrons at some point so that I can let it pass through the specimen. So I need some source of electron gun. So electrons are basically generated out here, and after that they have to be accelerated, so that at very high energy, so that they can come and interact with the material. So I have some sources of electrons, that can be either tungsten filament or lab 6 filament, or even the field emission gun. So I can get something called tungsten filament. It can also be lab 6 filament, or it can also be field emission gun. and depending on that, actually tungsten filament is is a low cost but lower emission source. Lab 6 can improve the intensity of the electron. Similarly, field emission gun can also enhance the intensity of electrons to a very drastic, very high extent, and the beam size also reduces to a very fine. So there are certain ways we can utilize all those sources of electrons to generate the electrons, so that they can come and react with the particular specimen. So once the electrons have been generated, I need to get a parallel beam of that, so that I can accelerate them. So that they have to be accelerated by a node, and after that they are basically parallel. They are made parallel, so that we can get a parallel beam, or they have to be made to fall on a very fine beam. So there is some set of magnetic lenses and certain apertures which will allow me to basically condense the beam, make it parallel, and then basically I can focus it further for imaging part. So I can get a parallel beam, so I can make it like a more like a micro probe. So I can get a micro probe beam of electrons. Again, I can also allow it to get convergent. So I can, instead of getting a parallel beam, I can make it converge, get a convergent beam for certain applications. So for probing, I need it like for scanning, tunneling, electron microscopy, I want a nano probe. Whereas for getting lattice fringe imaging or getting more diffraction patterns, I can more diffraction intersection of more Lowest zones at particular location. I can also utilize my convergent beam electron diffraction. So so there are certain ways I can utilize either to achieve a parallel beam or a convergent beam. So for that I need condenser lenses which can really direct my electron beam. So if I can direct my electron beam, if I can control the electron beam, I can get information what I am really looking for. Additionally, I can also tilt my electron beam to get a dark field imaging. So dark field transmission electron microscope imaging can also be attained once I have control on the condenser lenses, so that I can guide my electron beam. So that is the importance of the condenser lens systems, electromagnetic lens systems. And finally, the objective lens decides the overall resolution of the final image. And objective lens is one of the most important lenses, because it is generating the first intermediate image, and the quality of that will be essential to get the overall resolution. So once I am able to control the beam, that is good enough, but objective lens is the one which will collect the information from the specimen, and since it is also creating the first intermediate image, this is very critical factor in deciding the overall resolution of the final image. And in between, I can have diffraction or intermediate lenses, either to get a diffraction mode or an imaging mode, because they are being formed at a different locations. So I need to have two apertures or lenses which will guide me in terms of either switching from imaging to diffraction mode or being able to select a particular aperture. And there can be as well some projective lenses. They will magnify the second intermediate image. They can be either image or it can also be the diffraction pattern. And so projective lenses, they help in the magnification of the second intermediate image. Once I have formed my image and I have basically magnified it, I also need to see the image, because I can't see the electrons. So I need to see electrons, how they have interacted with the material. So either I can view them on a fluorescent screen, or I can also project it on some TV camera. I can also record it on either on a negative film, or I can also record it on a slow scan CCD camera. So these are required for the image observations, because we can't really see the electrons. So we will have to let it interact with the fluorescent screen, or see it on a TV camera, or I can also get it on a negative film, or I can also capture it on a slow scan CCD camera. So or it can also be on an imaging plate. So these are certain ways through which I can observe my particular image, and all these things are all the setup of TM involves interaction of electrons with the matter. So the traveling of electron is highly necessary, and that can happen because I am also looking for achieving a information which is elastically scattered electron. So I need to avoid any interaction of electron with the atmosphere. So for that I definitely need something called a vacuum system, because I want the electrons to pass through the beam through the particular channel without interacting with anything else, any of the atmosphere. If it interacts with the atmosphere, it is basically losing its energy, so that will become inelastic interaction. So to disallow any interaction of the matter with the gas So the gas particle should be absent in the column. So for that I definitely need a vacuum system, and here I require very high vacuum, which is approximately 10 to the power 6 to 10 to the power 7 minus 6 to 10 to the power minus 7 torr. So that part that much vacuum I require 10 to the power 6 to 10 to the power 7 minus 7 torr I require for the creating the vacuum. So this is very high vacuum which is being utilized out here. So for this I require very high vacuum, which is approximately 10 to the power minus 6 to 10 to the power minus torr, so that electrons can continue without any interaction with the nearby gases. So I can get an information which is truly from the interaction with the specimen, and I can achieve my vacuum by utilizing a pre-rotary pump, which is some sort of a pre-vacuum pump, and later on I can go for a diffusion pump or a ion getter pump to create such high vacuum. So that is what is highly required for a TM imaging. So here we see that we require a projective lenses for magnifying the second intermediate image, and then for visualizing the image I need to have some sort of a TV camera or a CCD camera, or I can also record it on an imaging plate, or I can also have it look it on a negative film. And since everything is happening with the electrons, the electrons need not get interacted with the nearby gases. So I need to allow a vacuum to be there, so I get information only which is truly from the material. So vacuum to the order of 10 to the power minus 6 to 10 to the power minus 7 torr is required, and which I can attain either by utilizing a pre-vacuum rotary pump, or followed it backing it up with diffusion pump or a ion getter pump, which become the main source for creating the vacuum. So coming back to the picture skew view of the electron gun, I have my filament. This can be either tungsten filament or a lab 6 filament. So this becomes my source of electrons. I apply certain bias to it, and I generate electrons. Once electrons are being generated, my Wiener cylinder, it has a negative potential. So once the electrons are being generated, it is now basically focusing the electrons to some particular spot. So that's what is being done by the negative potential out here, that I am generating my electrons. Electrons are negatively charged particles, and they now get focused or they get repelled by the negative bias, and from here they are now accelerated, because as a note I apply certain potential, positive potential. So now I help the electrons to accelerate to finally get a electron beam. So in this particular case I can utilize tungsten or lab 6 filament or even field emission gun as my electron source. I apply certain negative bias to basically construct my electron beam. Later on I can create some positive potential, so that electrons can get attracted and they can get accelerated to finally I can get my electron beam. And the sample preparation, it is very highly critical, because I need to make my sample truly transparent to electrons. And this is how overall construct of TM looks like. I have my electron gun to supply me electrons. Then I have set of condenser apertures and condenser lenses, which basically focus the beam or control the beam. I can get either parallel or a convergent beam. Then here is my specimen port, where I keep my specimen. Then I have certain objective aperture, which collect the light from the specimen. I have objective lenses. Again I have some diffraction lenses or intermediate lenses, and again some projector lenses to finally be able to observe it on a fluorescent screen or a image recording system. So that is the overall construct of my transmission electron microscope. But again here the very much requirement is of the sample to be transparent to the electrons. So generally we have some sort of holders which can either provide me a tilt in case when I require it. It can be up down tilt, it can be a side tilt, or it can also be a rotation which I can get from the holder itself. So this is what it is out here, that I keep my sample on a particular copper grid, and it has some locking ring on which I keep my sample, which is approximately 3 millimeter in diameter. So I can keep my powder, I can make a very thin film which is approximately 3 millimeter in diameter, but which the center part of that is transparent to electrons. I can also have some powders which are very fine enough, and those are basically transparent to electrons. But to prepare a sample, it is very critical to attain transparency to electrons. What I can do, since my samples will be mostly bulk in nature, so even to select a particular piece of sample from a bulk is very challenging, because first of all my sample has to be representative of the overall bulk structure what I really intend to look at. In say for an example, I am extruding a particular rod. So the structure at the surface will undergo much more shear. So the grain refinement might occur much more at the surface, whereas the grains may remain unaltered at the core. So if I am taking my sample only from the surface and I say it to be representative of what is happening in the core of that particular rod, I am totally wrong. So I need to carefully select my sample as such and then be able to relate it to the particular surface or particular area where I have taken my sample from. So I might require sample either from the surface as well as from the core to be able to say what is happening at the surface and what is happening inside the core of that particular rod. So once I want my sample to be representative of the particular bulk material, so I will take so many samples like from the surface as well as from the core, because what I am seeing in TM is only a very refined or very small regime of the overall bulk. So I need to very carefully select the region or the sample which is representative, truly representative of my overall bulk material. But so in order to make my material very fine or transparent to electrons, initially my samples may not be transparent to electrons. So what I will do, I will first of all I will section my material into very fine slices, which might be approximately a millimeter or less than that, maybe a couple of microns, as fine as I can cut them through a saw. Then I will start thinning my sample from say less than from more than which is greater than micron, maybe say approximately 100 micrometer in thickness. I start thinning it down to less than 1 micrometer. So once I have a particular disc, a particular sample which is less than 1 micrometer, I will punch out a small regime which is approximately 3 millimeter in diameter and its thickness will be less than 1 micrometer. So I will attain a disc which is approximately 1 micron and then less than 1 micrometer thin. Once I have this particular disc, I start thinning it mechanically. So I start thinning it down mechanically, and I can keep mechanically thinning it till it has reached much lesser than approximately 200 nanometers, or even as fine as I can go. So what I will have is a thin disc which is approximately 100 to 200 nanometer in thickness. If the sample is conducting, I can apply some corrosive or some media which can start eating away this particular material. So what I can get is I can start throwing some media. This is an enlarged view. I can start throwing in some media from both the sides until it starts eating away the material and creates a very fine hole in the center of the disc. So what I eventually get is more like this. I get a material which is a very fine hole in the center. So this particular point is nothing but a hole, and just the area nearby this particular hole is now transparent to electrons. So ideally, if I see it, it will be more like this. It will be transparent to electrons. So this is what I am really targeting at, to get a material which is transparent to electrons. Or I can also utilize something called ion beam milling. This is for conductive samples. I can use something called twin jet polishing. I am sending 2 jets on one on each side to start eating away the material and make it transparent to electrons at the center. Once I create a hole, the part near the hole is transparent to electrons. So seeing it from the top view, I can also this particular thing will look more like this, that I have a disc which is a hole in the center. So that particular hole, just the area nearby that particular hole is now transparent to electrons. So that I can create by twin jet polishing, or alternately I can also supply some ion beam. I will take a source of argon. I can start throwing my ions on the sample, and I start rotating my sample. So I can create a similar way. I can create a hole in the center, and on the region near this particular hole is again transparent to electrons. So I can look around in this particular regime to learn more about the sample itself. So there are certain ways. So my overall disc diameter remains around 3 millimeter, but the central part is now, it has a certain hole in it, and the area nearby that particular hole is now transparent to electrons, and I utilize that particular area to be observed or to be analyzed under transmission electron microscope. So I can see how critical particular sample preparation is, that I need to make the sample big enough so that I can handle it. At the same time, some part of it or the center part of it has to be transferred into electrons. So I can see or visualize or observe or analyze the region in that particular regime. So that's what is the overall thing about the sample preparation in the transmission electron microscope. And once my sample is ready, I insert it in the particular TEM holder or the transmission electron microscope holder, so I can observe it further. And how the overall magnetic lens looks like is, I have a magnetic lens which consists of a copper wire with some iron pole pieces. So what I am seeing is copper wires which are out these, and these are nothing but the pole pieces of iron, and once I supply some electric current to it, it will start creating a magnetic field. So I'll get some magnetic field which are represented by this red lines, and so what I can do, I can get a rotationally symmetric magnetic field, but this is again inhomogeneous, because I'll get a weak field in the center and very strong field in the on the sides near the pole pieces. So what I can see is, if my electron is passing through it, electron will basically get strongly deflected once it undergoes a very high field. So once the electron is traversing along this near the pole piece, it will get deflected very sharply, whereas an electron passing in the center will be deflected to a very lesser extent. So I can see that they will undergo a kind of a crossover, so they may not get focused at the same point. So that actually results that the electrons which are close to the center, they are less strongly deflected than those passing the lens from the far from the axis. So far from axis they get deflected very quickly, whereas in the center they keep going to much farther extent and they get deflected to a very small extent. So instead of getting a parallel beam, so we can try to focus all this beam into a spot, and this spot now becomes it is called so-called crossover, because I have a particular regime. Instead of a spot, it is more like a regime on which my electrons are basically being targeted or being focused at. So I get, instead of getting a very fine spot, I get a kind of a spot or a region which is called a crossover, and that happens because I have my electromagnetic lenses, and they create a stronger field near the pole piece, and the weak field is much weaker at the center part. So electrons which are traveling at the center, they get deflected to a smaller extent as compared to the near the pole pieces. So I can get some, instead of getting a very fine or a single spot, I get some sort of a regime, and that is called a crossover of the electron beam. And since it is a magnetic field which is being applied, so the electrons will experience a Lorentzian force, and since Lorentzian force is a component of the electric field as well as the magnetic field, and it also depends on the charge by velocity ratio of the electrons. So basically this particular part is more like this, that I am applying, I am letting the electrons get accelerate, I am applying a electric field, I am applying a magnetic field. So ideally with the magnetic field which is being controlled by a coil current, it results in some sort of force which is perpendicular both to velocity part as well as the magnetic part. So what happens, that basically is trying to pull the electron, at the same time it is trying to push the electron to certain direction. So that creates a helical trajectory, because my electron is traveling like this, and at the same time I am trying to pull it, or I am also trying to push it depending on the kind of field I apply. So my magnetic lenses, they are resulting some forces which are perpendicular to V. So I have some forces which are perpendicular to V as well as my B. So I can get a more like a helical trajectory. So electrons will traverse more like an helicity once they are traversing in a magnetic field. So I can see that the magnetic rotation is caused with respect to the object. So that basically is very essential, because depending on the kind of magnetic field I am applying, it will tend to rotate my image, because electrons, the way they are flowing, if they are very stronger field, they might get deflected to a larger extent. If I am applying a very smaller magnetic field, they might get deflected to a lesser extent, and that is nothing but my magnification, because I am applying field very strongly, I am allowing to form a very bigger image. So my image can also get rotated once I am applying a certain field. So this is one of the very important points in TEM, that electrons are traversing a helical trajectory. That depends on the magnetic field which is being applied, because that magnetic field is strongly creates a force which is perpendicular to both the velocity and the B part of it, or the magnetic field part of it. So that eventually forms a helical trajectory, and then it creates some sort of a rotation of the object itself. So the features of TM, they basically involve like this, that my electrons are interacting with the material either inelastically or elastically, but I want to avoid the inelastic scattering, because it is not containing an information. It is similar to like leading to absorption, because I am applying a certain electron beam, I know its energy, I know what are its features, and if it starts getting scattered inelastically, I don't know what kind of losses it has gone through once it has interacted inelastically. And after its diffraction with the material, I am getting some information, but I don't know how it is being generated. What was the incident energy of the electrons? So I always need to avoid what is happening inelastically, because it won't contain any local information. But if I am letting it elastically interact, or elastic diffraction can occur, then basically I can also modulate its either amplitude or its phase with the primary beam. So I can get both the information from either defects or the lattices. From that I can get what is the kind of amplitude change or what is the kind of phase change with respect to the primary beam, and so I can get information, I can extract the information from the diffracted beams what is happening locally. So that is the advantage of my elastic scattering with the material. I can avoid, so I need to avoid the inelastic scattering part of it. And again, the energy which is basically what I am utilizing in the TM is approximately 100 to 400 kV to result me a evolved sphere which has an inverse radius of 2 picometers, and these days we can go energy as high as 1.5 mega EV. So that in that particular cases I can have sample which is even more than a micrometer in thickness. So that part basically decides the overall energy which can pass through the material. So conventionally, or these days we generally utilize energy which is approximately 100 to 400 kV, and that is enough for giving us a good information. But instruments as high as 1.5 MeV are available, which can penetrate down to penetrate into a material which is approximately more than 1 micrometer in thickness. But generally the thickness of specimen has to be approximately 10 nanometer, or maybe the lesser the better. And again, my resolution part depends on the thickness. And again, if you want to get a high resolution TM imaging, that basically for that particularly we need to have the specimen to be thin enough, approximately nanometer in thickness, so I can extract much more information in terms of its lattice fringes or high resolution grain boundary imaging and so on. So overall features of TM are that I need to get, I need to avoid the inelastic scattering, I need to get the elastic scattering, and from that I can extract the information either for the lattices or for the defects, and then I can measure either the amplitude or the phase, and I can tell what is happening locally in the particular material. The overall energy, the electron beam energy, what is being interacted with the material, that generally is approximately 100 to 400 keV, and for that we need to have a specimen thin, approximately 10 nanometer. And then these days some other instruments are also available which can increase the energy to 1.5 MeV, and for that my sample size can be as thick as 1 micron. And for high resolution imaging, I definitely need to have a material which is thin enough, less than couple of nanometers. So coming back to the ray diagram, I can see that my specimen lies here, and then I have my back focal plane. Then I have my intermediate image which is forming. Then I have some intermediate lenses, and then finally I get my image on the either as an image or as a diffraction pattern. I can have a screen. So that is what is required out here, that I can selectively take a particular beam in back focal plane. I can allow only the transmitted beam to pass through, or I can also allow only the diffracted beam to pass through. So if I am allowing only my transmitted beam to pass through, what I get is something called bright field image. Bright field image. Or if I let only one of the diffracted beams to pass through, what I get is something called dark field image. So if I choose a particular aperture, back focal plane aperture, through which I am letting only my transmitted beam to pass through, I get something called bright field image. If I let only one of the diffracted beams to pass through, what I get is a dark field image. And conversely, I can look at a certain particular area. If I have particular microstructure in the bright field imaging, say I had a particular kind of a particular image which is being formed in the bright field image, and if I want to see what, say these can be very different phases. This can be phase A, this can be phase B, and to confirm that I need to get a diffraction pattern, because diffraction pattern is arriving from the elastic interaction of the beam with the material. So if I want to see what is this particular phase, say I want to see what this particular phase is, so I can let my beam concentrate on this particular part, and it can give me a diffraction pattern. So I can get a particular diffraction pattern that will be consistent to the kind of orientation. So I can again tilt my particular sample to get a different orientation, because within a tilt of few degrees I can get diffraction patterns from any different planes. So I can get diffraction pattern depending on the orientation of this particular crystal. So if I can align my beam according to this particular phase, I can get some diffraction pattern. So I can do that part as well, or I can go back to it more like this, that I can select one of the diffracting spots. If I take an area, and I can take a bigger area instead of a small focused regime, I can have an aperture which can accommodate more number of grains out there. If I choose say this much area which has more number of grains, and I am getting some diffracting spots, alternately I can choose a particular diffracted spot, I put my aperture here, and then I can again come back and see that this diffraction spot is resulting because of which particular grain. So which all those particular grains which are contributing to diffraction spot will start appearing brighter, and this thing is called dark field imaging, because I am letting only one of the diffracted spots to pass through, and only certain areas which are contributing to my this of my diffraction spot, because they are oriented favorably, they will start appearing bright, and rest of the field will be nothing but, so I have a dark field but my features are bright, which are resulting this particular diffraction spot, and this thing is called dark field imaging. So that part I can achieve with the transmission electron microscope. I can either get an image, or I can also get a information about a particular crystal through its diffraction. So that is the overall capability of my transmission electron microscope. So eventually what we can see, I have my backfocal plane. This gives me a diffraction pattern out here, and if I keep my aperture somewhere, I can get either a bright field image if I let my transmitted beam pass through, or if I let my diffracted beam pass through, I can get some image, and that will be the dark field image. Or if I can put my aperture at this particular location, which is nothing but a Gaussian image plane, and that will eventually form a diffraction pattern. So I can see that in transmission electron microscopy, I am capturing the beam which is passing through the material. So my particular specimen or the sample is to be transparent to electrons. So if I am using something which is much thicker, through which electrons can't pass through, I will not get any information. So the information like secondary electrons, backscatter electrons, they have to be collected back, like not through the material, but back on the surface of the particular material or the sample. But in transmission electron microscopy, I make the sample thin enough so my electrons can pass through and they can interact with the material elastically, and then I get the information. So for the diffraction, the planes have to be almost parallel to the incident beam, and then they get diffracted within a regime of 0 to 1 degree. So I can see that for a particular plane to be aligned, I have to tilt it to a very marginal extent, so that I can align it, and I can get a diffraction pattern from that particular plane. And again, the zone axis becomes the incident beam itself. That the direction of incident beam becomes the zone axis of the planes which are diffracting which are basically diffracting the electron beam. So I can see that the zone axis of that the incident beam itself becomes the zone axis. And then again, the sample preparation is very critical, because for electrons to pass through, they need to basically interact with the material, and the sample itself should be thin, that the energy which is being supplied to the electron is enough for it to come out of the material. So that is the requirement for that. And again, my evolved swirl becomes so huge in comparison to that of which is constructed in the X-ray diffraction, that now my evolved sphere can touch more number of points in the reciprocal lattice spacing. So more number of planes basically produce a diffraction pattern, and now I can analyze the diffraction pattern to come out with what is the overall material, or how the basically what is the overall phase which is present out there in my particular material. At the same time, I can get an image. I can see the crystalline nature of the material. I can also focus a nanocrystalline grain itself, and I can get some information out of it. Or I can do a vice versa, that from a particular diffraction pattern, I can look which all grains are oriented favorably to my incident beam. So I can see these kind of things in the transmission electron microscope. And there is much more to be explored, which I will basically cover in part 2, and I end my this particular lecture here. Thanks a lot.